Alright, so let's keep talking about finding area underneath some functions. And so to begin, we're just going to start with some conditions. We're going to agree that we're on a set D, and various places during this during the videos here, you're going to see me actually use R, so we can use R instead of D. Doesn't much matter. I'm going to stick with D as that's what I have on the slide. So it's a two-dimensional input function, one-dimensional output. It's continuous and it's non-negative on a closed rectangle. Okay, so we talked about closed end topology, all that already. And so we're going to say it's on this rectangle, and then this is how we're going to denote it. So visually, you might expect to see it something like this, it represented in two dimensions. And again, this is the input, so we're allowing any input within this rectangle, and then the output could be something else. Okay, and also throughout this video, we're going to use this example here. So f of xy is equal to 6 minus x squared minus y squared on that particular domain. And so, again, just to visualize the domain, we have this green region down here shaded. So x can go from 0 to 2, y can go from 0 to 1, and then when we visualize the surface on this particular region, that's the image that we get off to the right. Okay, so we're still kind of interested in finding the area underneath this surface on this particular domain. And so we remember that going back to Calc 1, we talked about this idea of creating a partition and looking at a particular value, and then creating a partition, looking at a particular value, and then creating little estimating rectangles. So we're going to do that eventually. I want to introduce a different method, and it's an idea of slicing. And so you can look this up. It's called Cavalieri's principle, and it just details the method of slicing. And so we're going to kind of walk through that idea right now, or how we're going to use that idea rather. So if we fix a particular value, and it I'm just going to say x is equal to x0. Okay, so it could be some fixed constant in our domain, certainly. What is the area of that slice? So first, let's visualize it. So if I have this maybe, I don't know, let's say here. Okay, so that's going to be my x0. So closer to 2 than to 0. So maybe it's, I don't know, maybe it's this slice right along here. And so what I would visualize this as is, here's the slice, and it's going down and back. I can't really see that part, but then it would extend something like this. Okay, so it's this little slice in here. Okay, and that's x0. Okay, so what I want to do is, and that's not going to show too well. Let's see if I can get a different color. Let's use pink. Is pink going to show? Oh, beautifully. Okay, there we go. There's our slice. So what's the area of that slice? Okay, well, let's do some thinking. So I have area of x0. Okay, well, based on my previous knowledge, I know that if I think about this, it could be represented as the function of x0 comma y. Okay, that would be the height where I meet that surface, and then that would give me the height, but then I need to certainly allow the function to range. I'm keeping x0 fixed, but y is still variable. Y is still changing from 0 to 1, so that means I need to go from 0 to 1 of the function dy while holding x0 constant. Okay, or x constant at x0. Okay, so that should be the area of the slice. Alright, so now this is just Calc 1, and so now I've taken the area of that slice, but I'm still interested in the entire area underneath the surface, not just that slice. This slice is infinitely thin, and we're going to say it's thin with a thickness of delta x, or dx, that we'll see later. And so if we think about the volume of that slice, it should just be a of x naught and then delta x, okay, that would be the volume of that slice. And so now if I sum over all possible slices, that is to say the volume is a of x, and then we can represent this as dx if I integrate over all possible slices, which go from 0 to 2 for dx. So I'm moving that slice now through all possible ranges of x. So this is to say that I get the integral from 0 to 2, and then of the integral 0 to 1, and then f of x, y, okay, and I'm not inserting x naught here because x is actually changing as well on the outer integral. Okay, so that should be how I can find the volume of my figure. So let's go ahead and do that with our example. Okay, so the area, okay, again, if I think of a slice, okay, I'll draw that here again. Okay, here's my slice. And then down, and then in. Okay, so I said that the area was the integral from 0 to 1 of, and then the function, so 6 minus x squared minus y squared, and then dy, okay. And I'm going to let you crank that down. What I got was 17/3 minus x squared when I did that. Okay, and then proceeding right on to volume. Okay, well now volume would be the integral, and then now this is allowing x to range from 0 to 2 of my area function, so 17/3 minus x squared dx, and what I got with this was 26/3. Okay, so Cavalieri's method really is a nice way of finding the area underneath a function. Okay, using slicing. From Calc 1, we did discuss the idea of integral or Riemann sums and that sort of approach. We do get there eventually, but this is an alternative approach to finding a volume.